Imagine standing beside a sink. In front of you is a touchscreen that controls the temperature of the water. If you press option 1, you get cold water. Option 2 gives you warm water, and option 3 gives hot water. This setup gives us a perfect real-world example of a function. For every input, there is exactly one output. That consistency is what defines a function. In this case, the input is the option we select, and the output is the temperature of the water. In mathematical terms, the option input is the independent variable because we control it, and the temperature is the dependent variable because it depends entirely on which option is selected. Now, in our example, we have a strict selection for the input. Option 1, option 2, or option 3. That's it. No hidden inputs, no secret settings, and definitely no fourth option. This complete list of values we're allowed to put in is called the domain. Since our input is limited to just these 3 options, the domain is fixed. As a result, the system can only produce a specific set of outcomes, in our case, cold, warm, and hot. This set of possible outputs is called the range. Now, let's change the setup a little bit. Instead of simply labeling the options as cold, warm, and hot, each option now displays the exact temperature of the water. Let's take this one step further and bring time into the picture. Suppose the input is initially set to cold, and the water temperature is steady at 60 degrees Fahrenheit. You tap the hot option. The temperature does not jump instantly to 110 degrees Fahrenheit. Instead, it rises gradually. As time passes, the temperature increases until it finally levels off at 110 degrees Fahrenheit. On a graph of temperature versus time, as the time increases, the graph will rise from left to right. So here we say the function is increasing over this interval. Now, if we tap cold again, the water will begin to cool gradually. As time increases, the temperature decreases steadily until it settles back at 60 degrees Fahrenheit. On the graph, time is still increasing, but the temperature values are going down. So over this interval, we say that the function is decreasing. Now look more closely at the shape of the graph. Notice how the temperature rises quickly at first and then slows as it approaches 110 degrees Fahrenheit. This is the rate of change, also called as the slope. It tells us how fast the temperature is increasing or decreasing at a given moment. If you look here, when the temperature is rising quickly, the graph is steep and the rate of change is positive and large. But when the temperature is rising more slowly, the graph becomes less steep. Here, the rate of change is still positive, but smaller. If we look at this entire region again, we can see that our rate of change is going from a larger value to a smaller value. So we can say that the rate of change here is decreasing. Similarly, when the temperature is falling quickly, the graph is steep. The rate of change here is negative and large in magnitude. And when the temperature is falling more slowly, the rate of change is still negative, but smaller. So we can say that the rate of change here is increasing because it's going from a larger negative value to a smaller negative value. Now let's take a look at the bending behavior of the graph. Here, the graph bends downward. This is called concave down. And when the graph bends upwards, it's called concave up. Now there is a precise moment during the temperature change. When the graph switches its bending behavior, either from concave up to concave down, or vice versa. That moment is called the point of inflection. When the dependent variable is greater than 0, the graph of the function lies above the x-axis. In this interval, we say the function is positive. And when the dependent variable is less than 0, the graph lies below the x-axis. In this interval, the function is negative. But right here, when the dependent variable is exactly 0, the function is neither positive nor negative. These points are called the x-intercepts, or the zeros of the function. So far, we've analyzed how a function behaves. Now let's take a look at different ways of representing that function. First is the graphical representation. This is the visual form. It shows us how the function behaves at a glance. Second is the analytical representation. This is the formula that defines the function. It gives us the exact mathematical rule that produces the output from the input. Third, numerical representation, or the table. Here we list specific input and output values. And finally, we have verbal representation. This is where we describe the function in words, explaining what it's doing, how it changes, and what it means in context.